All right, we're on chapter 2 of Linux device drivers, building and running modules. It's almost time to begin programming. This chapter introduces the essential concepts about modules and kernel programming. In these few pages, we build and run a complete, if relatively useless, module, and look at some of the basic code shared by all modules. Developing such expertise is an essential foundation for any kind of modularized driver. To avoid throwing in too many concepts at once, this chapter talks about modules without referring to any specific device class. All the kernel items, functions, variables, header files, and macros that are introduced here are described in a reference section at the end of this chapter. So setting up your test system. Starting with this chapter, we present example modules to demonstrate programming concepts. All of these examples are available on O'Reilly's FTP site, as explained in Chapter 1. Building, loading, and modifying these examples are a good way to improve your understanding of how drivers work and interact with the kernel. The example modules should work with almost any 2.6x kernel, including those provided by distribution vendors. However, we recommend that you obtain a mainline kernel directly from the kernel.org mirror network and install it on your own system. Vendor kernels can be heavily patched and divergent from the mainline. At times, vendor patches can change the kernel API as seen by device drivers. So after reading that, I was curious about specific vendors and how they may change the kernel. So I asked ChatGPT about that, asking it to focus on Red Hat and Linux, Rocky Linux. ChatGPT says they often apply extensive patches to the Linux kernel, creating significant differences from the mainline or vanilla kernel developed by the Linux community. So let's scroll down past the generic information. I don't need to know why they change it. I want to know what they are changing. So here's the types of kernel modifications by Red Hat, and apparently these are going to be inherited by Rocky. So backporting features and fixes is one type. Red Hat backports features and bug fixes from newer kernels to older kernel versions that have deemed stable for production use. This approach allows Red Hat and Rocky to provide advanced features without updating the entire kernel version. I want to know what the advanced features are. Okay, here we go. For example, support for a newer file system feature or a networking improvement from a kernel like 5.10 to their default kernel version 4.18 in RHEL 8. Oh, that's fascinating. So the kernel is still going to report itself as 4.18 when you're using RHEL 8, even though something from kernel 5.10 is in it. I think I'm reading or interpreting this correctly. Another type is enhanced security. Red Hat often implements additional security features and patches such as Spectre and Meltdown mitigations, App Armor, SE Linux enhancements, and custom sandboxing features. These mods may impact the APIs available to device drivers, requiring device driver adjustment to handle Red Hat's security-oriented changes. Red Hat's kernel might also introduce specific security policies and system calls not found in the mainline kernel, and device drivers need to comply with enhanced security modules. So I'm going to ask him to tell me more about this. So this specifically is interesting to me. Red Hat often implements even unique system calls to reinforce the security of its kernel, specifically catering to enterprise environments. These modifications are typically found in Red Hat's version of the LSM and SE Linux, along with custom system calls. Oh, here in a second I'll ask them, can you identify these custom system calls, even though they might later down in this text. So example, SE Linux, a powerful access control system, enforces strict permission on resources and processes. In Red Hat's kernel, SE Linux is often configured with more stringent policies than those found in mainline distributions. Okay, so we're talking about a difference in kernel configuration. Driver impact. Imagine a network device driver that performs certain privileged operations like adjusting network interfaces or accessing hardware registers. In Red Hat's kernel, SE Linux may enforce additional access control hooks to restrict these operations based on predefined security contexts, even if the device driver assumes access is allowed. Okay, so the driver developer may assume that. Doesn't mean the kernel, in Red Hat at least, will be okay with it. Red Hat sometimes introduces these custom system calls like memory management or cryptographic operations. So one example is SecComp, Secure Computing Mode. It's a facility. So the driver impact of this custom system call, let's say a device driver for a security appliance needs to interact with memory in specific ways, such as locking pages in memory for sensitive data processing. In Red Hat's kernel, SecComp or similar calls may include additional restrictions to limit memory access. These restrictions that only processes with explicit permissions can use certain memory or encryption functions. So in terms of compliance needs, the driver must be coded to work with this SecComp restricted system calls, meaning it may need to use alternative or additional system calls or run in a specific security context set by the SecComp profile in Red Hat's kernel. In this section, they talk about enhanced access control lists. Red Hat enforces stricter access control lists for certain kernel resources, particularly with device files and network sockets. For example, device drivers that attempt to open specific device files might be restricted by Red Hat's policies on the dev file access permissions. So, driver impact, consider a driver that interacts with specific hardware devices mapped under that location, such as a dev mem for accessing raw memory. Red Hat's kernel often disables or restricts access to such device files to prevent unprivileged processes from accessing sensitive memory. This restriction prevents a driver from performing operations it could normally perform in the mainline kernel. Oh, I want to read about C groups, so before jumping back, one more. Certain system calls or kernel functions are restricted based on the C group and SE Linux label of the process making the call. So imagine a storage driver that handles I/O operations for high throughput data. It might allocate large buffers or set certain resource limits. Red Hat's kernel may restrict these allocations to protect system stability and prevent resource abuse. The storage driver must comply with these resource limits or be configured to run under the appropriate C group. Interesting, and that's for a storage driver. Okay, so I still hit send on that question. So just to see if there's more than just this SecComp, Secure Computing Mode system call. Oh, and I found out more details about that particular one. This system call allows Red Hat to limit certain privileged calls on a per process basis, often used to sandbox applications like container runtimes. For example, Podman, with stricter rules than the mainline kernel. Okay, but I wanted to see more custom syscalls. So here's another one, process control. This call is used to manage process level attributes, including capabilities that control access to certain system level functions. Red Hat's kernel might enforce stricter checks or add additional capabilities under SE Linux, specifically restricting what certain processes can perform even when or if they have partial privileges. So it'd be interesting to see when that syscall is being used on a system. Another one is BPF, Berkeley Packet Filter. Red Hat has optimized and sometimes extends support for eBPF, extended BPF, to allow for secure in-kernel filtering and monitoring. When I think of eBPF, I think of kernel monitoring. They say in rail environments, BPF is often used for system observability, security monitoring, and enforcing access controls within networking. And then they give us some various system calls, including setX attribute, getX attribute, and other file attribute related syscalls. This is for more granular control over extended file attributes. So these calls may enforce additional SE Linux context checks beyond what is standard. Oh, and down here we have 5 modified network namespace and C group related syscalls. So UN share, set NS for namespace, I assume, and then clone. In environments with SE Linux enabled, these might enforce additional permission checks. Okay, let's get back to our book. So sure, vendor kernels can be heavily patched. If you are writing a driver that must work on a particular distribution, you'll certainly want to build and test against the relevant kernels. But for the purpose of learning about driver writing, a standard kernel is best. So I wonder if Red Hat open sources their kernel, like you could see the modifications they've done to it. Maybe they have a changelog for us to read. Okay, it looks like you can use this command, rpm-q-changelog kernel. So when I tried that command out, it was crazy long. So I asked for a URL. Looks like we need a Red Hat subscription to access it. If anybody watching has more experience with this, let us know in the comments below. Regardless of the origin of your kernel, building modules for 2.6x requires that you have a configured and built kernel tree on your system. This requirement is a change from previous versions of the kernel where a current set of header files was sufficient. 2.6 modules are linked against object files found in the kernel source tree, and the result is a more robust module loader, but also the requirement that those object files be available. So your first order of business is to come up with a kernel source tree, either from the kernel.org network or your distributor's kernel source package. Build a new kernel and install it on your system. For reasons we'll see later, life is generally easier if you are actually running the target kernel when you build your modules, though this is not required. So we got a little bear trap here. You should also give some thought to where you do your module experimentation, development, and testing. We have done our best to make our example modules safe and correct, but the possibility of bugs is always present. Faults in kernel code can bring about the demise of a user process, occasionally the entire system. They do not normally create more serious problems, such as disk corruption. Nonetheless, it is advisable to do your kernel experimentation on a system that does not contain data that you cannot afford to lose, and that does not perform essential services. Kernel hackers typically keep a sacrificial system around for the purpose of testing new code. So if you do not have a suitable system with a configured and built kernel source tree on disk, now would be a good time to set that up. We'll wait. Once that task is taken care of, you'll be ready to start playing with kernel modules. And so I'll begin the next video in a part 2 here with the Hello World module.